Hello, everyone. Today, we're presenting our study on the paper titled Requirements Classification for Traceability Link Recovery. And this research focuses on enhancing the precision of traceability link recovery, or TLR, between software requirements and source code using an advanced large language model called Norbert, combined with an existing method called FTLR. Our group members are me, Morgan, Pavani, and Manas. So let's start by discussing why this research is important. Next slide. So in software engineering, traceability refers to the ability to trace and link various artifacts, such as requirements, design documents, and code. This is crucial for ensuring that requirements are properly implemented, tested, and maintained. It's particularly important to safety critical systems like automotive or aerospace, where traceability is required by regulatory bodies. Now, manual traceability is a labor intensive process, and as software systems grow in size and complexity, it becomes nearly impossible to manually trace these relationships. So this introduces a need for automated approaches to recover traceability links. The problem is most existing automated approaches suffer from low precision. They often include irrelevant or unnecessary parts of the requirements in their trace links, which reduces accuracy. And the motivation behind this research is to address this problem by using a large language model, Norbert, to classify and filter irrelevant parts of the requirements before recovering trace links. This improves the precision of TLR, making the process more reliable and efficient. Next slide, please. So what makes this research novel is its approach. It introduces Norbert, which is a machine learning model based on BERT, a well-known large language model that excels at understanding natural language. Norbert is fine-tuned to classify parts of software requirements, identifying which portions are relevant for traceability and which are not. The novelty doesn't stop at Norbert. This research also integrates with an existing method called FTLR, or fine-grained traceability link recovery. FTLR operates at a very detailed level, mapping smaller elements of requirements like individual sentences to code artifacts. The combination of Norbert's classification abilities with FTLR's fine-grained linking is what makes this particular approach unique and more effective than other methods. Next slide, please. So now let's dive into the methodology. This approach can be broken down into two parts. One part is Norbert and the other part is FTLR. So first we have Norbert, which is an adaptation of the BERT model, which is mentioned before, is trained on large text data sets like English Wikipedia. For this specific research, Norbert is fine-tuned to classify parts of requirements, such as functional aspects or user-related elements. It does this by analyzing the text of the requirements and determining which parts are actually relevant for mapping to source code. Then we have FTLR, which stands for fine-grained traceability link recovery. It operates by breaking down both requirements and source code into smaller components like individual sentences or method signatures. It uses word embeddings to calculate similarities between these smaller elements and create trace links. What's key here is that Norbert acts as a filter before FTLR is applied. And by filtering out irrelevant parts of the requirements, FTLR can operate more effectively and with greater precision because it's working with only the most relevant information. Next slide.
Here, the study emphasizes on performance of Norbert's classification model. So the objective of the empirical study is to evaluate Norbert's performance in classifying requirements elements and its potential to improve TLR by filtering irrelevant parts of the requirements by answering majorly two questions. First one, is it possible to transfer the performance of an LLM-based classification approach on unseen projects from whole requirements to requirement elements? And the second one, which Norbert configurations performs best on TLR datasets? So to provide answers, the model has been pre-trained using several data sets from ETOR, iTrust, SMOS, EANSI, and LibEst, which are commonly used in TLR research. And requirements elements were manually labeled for functional aspects, user-related, function, data, and behavior concerns to establish a gold standard. So here, ETOR, EANSI, and SMOS consist of use case descriptions. iTrust includes only flow of events of use case descriptions, while libest has only textual requirements. Next slide, please. Here, the class distribution across projects is shown in this table 1. So splitting requirements into requirements elements results in a significant increase in data points for classification, totaling 3,284 elements. For example, EANSI project has 139 use case descriptions that contains almost 1290 elements, representing over a third of the total elements. However, only 874 of EANSI's elements include functional aspects, meaning that 416 elements needs to be filtered out. Similarly, iTrust dataset, which only includes flow of events descriptions as requirements, produces 336 elements from the original 131 requirements. Next slide, please. Here, for the experiment, a leave one project out cross-validation strategy was employed to evaluate performance on unseen projects with maximum amount of training data for each project while excluding the project being tested, thereby ensuring generalizability. So, accuracy and F1 score were used to evaluate the overall classification performance, considering both unweighted and weighted average by class occurrences. So, the reason for choosing F1 score is it's particularly important for balancing precision and recall. So measuring both accuracy and F1 score offers a more comprehensive view of binary classification results, especially in handling overlapping classes. Next slide, please. Here we will discuss the evaluation results for Norbert. Table 3 shows the resulting accuracy, which is shown in previous slide, and Table 4 shows precision, recall, and F1 scores across the projects and their classes. So in this experiment, Norbert achieved a weighted accuracy of 84% for identifying functional and user-related aspects, and over 70% for function, behavior, and data concerns. For example, to identify functional aspects in ETOR and iTrust, the model was even achieved accuracies and F1 scores of over 90%. So here for this class, both unweighted average and weighted average are almost identical to with each other. So the classification results shows that Norbert is highly effective at classifying requirements elements on TLR data sets with comparable or even better performance than on whole requirements to answer the first question, requirement 1. So and the best performing configuration for Norbert was bet large with 16 epochs and oversampling for most of the classes, except for the function class, which performed best without oversampling to answer the second question. So, however, it encountered some challenges with unbalanced data sets and the use of machine translation for some requirements, which could introduce biases and errors during classification accuracy. Next slide, please.
Yep. So the FTL methodology. What is? Let's see some of the overviews of it. It breaks down both the requirements and code artifacts into smaller, precisable, and then traceable features. Just like we were discussing that Norbert helps to, I guess, filter out. Okay, and here it utilizes both the word embeddings and the word mover distance to establish similarities between requirements, elements, and code. And this is especially highlighted because this is a very important feature. And then, of course, it traces links back at class level. With the integration of Norbert, it filters out irrelevant requirements elements. This is the most important part. And filtering out paths improves trace links accuracy, and of course it reduces false positive. So with Norbert, it becomes way more accurate, very effective. So let's go to the next slide. Oops. Yep. Here are some of the evaluation results I did with like impact of Norbit on filter, and we can see from the chart that how it improves it improves overall when we were measuring it. It improves the FTLR's performance by around 0.8%. The filtering capability. F1 score compared to baseline FTR without filtering. So we can see Norbert with Norbert, it's much more effective. Using Norbert to filter out, it improves precision. Combining one more thing I just want to say, it's combining the filters for functional and user-related elements improve the overall F1 score to 40.7%, outperforming the state of the art. Let's go to the next slide. Okay, here are some of the insights we want to see for potential improvement overall on the paper, and to take it just much further. Is it one of the things are domain-specific fine-tuning? Fine-tune Norbit on a domain-specific data set, like medical, aerospace, just for examples. One more thing I want to touch on is the manual intervention. Introduce like semi-automated approach, especially for data sets with low precision, where false positive can just get out of its way. And of course, combine like LLMs with Norbit, so to capture just more complex relationship. We know how LLMs are very advanced nowadays, and if we combine them with Norbit with graphs-based methods, it will. I think it should capture more. It will go more in depth, and it will capture more complex. Last thing is we want to do is the conclusion. This is some of our summary. Norbit filtering out irrelevant paths to improve. We all know that. And the integration of classification and TLR methods offers a more automated and accurate solution to traceable task in software engineering. Future work, we'll say, is further research on scaling these methods to large and industrial data sets. One more thing we want to say is to extend this approach to other types of software architects beyond requirements and source codes, such as design documents and test cases. And this is some of our